get started. Actually, before we start, no need to take pictures of slides. You can download the PDF on this URL that's up there, and I'm going to repeat the URL on the last slide, so makes it easier. You don't have to take notes. So what I'm going to talk about today is really about the chaos that we all see, that we all experience now these days, because the business pursues agility and pushes for agility, and that all of a sudden ends up causes the business to realize that, hey, there are microservices we can use, right? And all of a sudden we see a lot of organic growth in the architecture. So what that does is, because as agility and microservices collide, we get something, and that's the key word of this title really, is the ecosystem of services. Now, that is something different from an application, right? It is decidedly not an application. It is a federation of services and applications. And it's typically something, because the business wants to be agile, it's something that evolves organically, right? And this leads to a new reality that I'm going to talk about, where the environment of an architecture, the environment of an application landscape, a service landscape, is really the determining factor of the success of a deployment. And I'm also going to talk about how we kind of all already live in that new reality, and what we can do about it, and so forth, obviously. And bottom line is that requires runtime control and a mission control approach to operations. So that sounds super abstract, everything. You're probably going to ask yourself, is this actually real? Does this exist? And so I'm going to go back and come with a story from old school IT, right? And this is one of these airline disasters, right, where something happens on the IT side, and for days passengers are grounded, planes are grounded, blood and tears in airports happens and stuff, things like that. And that's happened to Southwest Airlines, American Airline, in July of 2016, and one of the few incidents where it was actually reported was what happened, right? And in essence, what happened was that one out of a large number of routers in a Dallas NOC failed, right? And it didn't just fail; it failed in a really weird way, and it was monitored. It had tons of agents on it, all the lights were green, all functions were green, but billions of packets were coming in, not a single packet coming out, so it didn't route, right? So none of these monitors caught that. And it took the team just 30 minutes to find out that this router was the culprit, right? But that was enough time to completely shock the system. Other, neighboring systems were disconnected from data, disconnected from each other, were in a funky state. They had to start reboot these systems, right, for another 12 hours. And then, because these systems were not there were ripple effects happening for another 5 days until full recovery. So, critical data, like how long were these flight crews planned for? Is this still legal? Can we fly? All these things didn't work, right? 5 days of outage. One router, 5 days of outage, $80 million in direct losses, and almost $3.5 billion wiped off the market cap. Obviously, it's super dramatic, but really nice 3 learnings in that, right? Number one is this new reality where the entire environment determines how successful our applications and services are going to be, already exists, right? The second learning is that monitoring doesn't buy us anything if it's not at the right level of granularity and at the right level of the stack, right? And number 3, that even if I had this monitoring, I need an ability to control the interactions of systems, to be able to push back against things, to throttle things, to traffic shape in one shape or another, right? So this is the learning, and what I'm going to talk about in this talk, and what we're going to hear over and over again, are three key terms. Number one is like, if you think again back to business agility, driving microservices, a lot of organic growth, continuous growth, that leads to something we call a service landscape. Yeah? That is this ecosystem of services that that continues to evolve over time. Yeah? And this service landscape has a number of characteristics that pertain to stability, security, and predictability that really create a new reality for all of us. And that reality is that, as I indicated earlier, that the environment is really what matters, right? Much more than code. And I'm going to talk about how our existing approaches to deal with this new reality kind of fall short in a number of respects. So I'm going to talk about monitoring and tracing and all these kind of things. And then how we really need real-time remediation, really fast MTDR cycles, mean time to repair cycles, right? And that is something I'm going to call a mission control mindset. So this person here, some of you may know, is Gene Kranz. He's a flight director of the Apollo missions, most of the Apollo missions, the early ones, and including Apollo 13. So after that, I'm going to give some real-world examples, use cases, case studies, how architectures that are really dynamic can be remediated in real time and what that means, how that looks like. I'm going to give examples that are reactive, like react to incidents. I'm going to give examples that are a little bit more proactive. And then I'm going to close with takeaways for all of us, depending where you're on the journey of like adoption, acceptance for this chaos, what you can do on that journey, right? A little bit about myself. I'm Tobias Kunze. I'm the co-founder and CEO of a startup out of Silicon Valley called Glasnostic. And we provide enterprises with runtime control for these sprawling, organically growing federated systems. Before I founded this company, I was a tech co-founder of the company that became OpenShift. So I was fully concentrated on how can we optimally, support the building of applications. How can we host applications? It was a PaaS, right? How can we host applications? How can we get this, polished to the nth degree? And then, as OpenShift slowly became successful, gained traction, there were like two interesting learnings, right? Because we talked to a lot of customers, and number one was that successful applications are never just applications. They're always part of a federation of things, right? They're always embedded in a number of other applications. Not a single successful, meaningful application in enterprises is a standalone, like a 1996 web application type, where you have a web tier talking, or like a web tier talking to a database, and that's it, and not talking to anything else. It's always part of a federation. And the second learning was, by talking to these customers, how do they run these things and so forth, is that the successful applications or federations of applications were never successful because they were engineered well. They became successful because they were operated well. And that's something I want to keep repeating throughout this talk. Okay, let me zoom out for a minute and give a little bit of context. Where is this coming from? Why are we talking about this thing? Agility is super abstract, and is this actually really real? Does it happen? And yes, it does happen. We all know on the organization level, we work in small autonomous teams. We have super fast decision and learning cycles, right? So it's an agile organization. And what happened in the past 5-7 years is that we can now leverage a massive, vast cloud ecosystem for productivity, right? There's literally hundreds of Lego blocks that we can consume as a service, and there's cloud-native technologies that we can adopt, right? And all these things are being deployed in parallel by our two pizza teams, right? And what happens on the architecture layer in the middle, so to speak, is, right, we started evolving from the monolith, going to microservices, which most of the time meant it was a single application, right? Decomposed in a bunch of services, but still a single application, kind of a distributed application. And then more and more of these microservice applications started talking to each other. So we got base services, like shared services underneath, increasing complexity, obviously, and then slowly, with agility, this organic federated growth started happening, resulting in a service landscape. And that has a profound effect on the control layer that governs how we connect systems, right? We used to start with like old school enterprise integration, then move to APIs, proxies, gateways, these kind of things. Service mesh is a little bit of a newer occurrence here, and ultimately to something we call full-on traffic control. And it also had a profound effect on how we do operations. And those are not independent journeys, independent evolutions, right? And we may be on the different layers, we may be in different places, but what it represents is a truly new agile operating model, right? Where an agile organization leverages cloud, it creates new services, new capabilities for the business, all in parallel, which creates a service landscape. And we can now control and govern the service landscape in a way, the control and operations part of it, so that the business can adapt to the business needs in an agile manner, right? So that is really the new application. That's the new agile operating model that drives everything. And because that is our new model, it changes our architectures, right? It's something that's entirely unescapable. So just imagine a standard, like smallish microservice application. Doesn't matter what it is. The green things may be applications, yellow is SaaS, and there's data stores, there's an administrative application coming in from the top and so forth. But after a while, it evolves, right? It gets more services, more functionalities being added. Maybe there's a new partner integration. Maybe there's a mobile gateway, right? Then another application in the enterprise ecosystem, right, starts talking to it because it has useful data. So it taps into that data and so forth. More and more applications, services, capabilities built on top and next to these existing services, because that's what gives us speed, right? And now that is what a service landscape is, right? It's a continually evolving federation of services, right? And it's highly dynamic. It's a key characteristic of it, right? It's a landscape of federated services that is like highly connected and is an ecosystem. It's not a single application. And it has three key characteristics that are troublesome for DevOps and operations folks, right? Number one is security, right? On the architecture, if everything keeps moving around, there's no perimeter, right? Like, where should I start securing something? It's also, the architecture is dynamic. I don't have a static blueprint anymore, right? There isn't an architecture that is now still the same a month later, right? Because all this organic growth. And on the endpoint level, all these actors are moving around all the time. They come, they disappear, they appear again in a different guise and so forth. That creates a lot of like volatile behavior. Right? So the question is like, how can I secure this? And encryption and certificates is a good initial step, but the key problem is really the dynamic nature of all of that. Right? Second characteristic is the stability of it. Right? As I string together components, I get a lot of weird behaviors, right? Because each component behaves in a particular way, which I can't really necessarily foresee. So here's a little schematic. I'm going to come back to this example in my example section later. It's like, just imagine a little bit of net new organic growth being added to a landscape. That changes, let's say, the fan-out pattern and hits a cache. The cache now thrashes around. All of a sudden, there's unsystematic, asymptomatic slowness in a totally unrelated area of the landscape. Right? So what happens here is that these cascades of effects, right, are very large scale in nature. Right? Very complex. A lot of interactions take part in that. It's very difficult to disentangle, right? Causality, and any effect on one side of a service can turn into a totally different effect on the backside, on the upstream side of that service, right? So it becomes very nonlinear, right? So a deployment on one end is all of a sudden slowness there, and there was a cache involved in the middle, right? So that all makes it very unpredictable. Right? And that's, again, a fundamentally new challenge, right? So how can I stabilize that? And I want to drill a little bit further down into the third characteristic, predictability, because it is important to understand that in a system like that, that is as dynamic and isn't really designed upfront, we can't engineer our way out of these discontinuities, right? Any component that we add to this landscape has its own idiosyncrasies, its own surfaces, its own discontinuities, right? Its own limits. And every time we change the amount of traffic we give it, or the type of traffic, it can all of a sudden flip in a different state, right? It's kind of like shining a laser through a bunch of prisms, right? It's very difficult to predict the patterns. I mean, simple, if I take just one, it's easy, but if it's 50, it's very difficult, right? And they all influence each other. So what we typically see in these architectures is like people setting, runtime behavior in configuration. And that now becomes an anti-pattern, because any retries or any timeouts that are set in YAML, right, just becomes a new idiosyncrasy for that service now. Right? So another really important characteristic of that. Yeah. So we can't simply take runtime behavior and set it in configuration and then think that we can forget about it. So zooming back up to the service landscape, right? The key new reality here is, so the key problem is really that the agility that we want to support gives us an architectural style that we can't control. Right? It has stability, security, and predictability characteristics that are very difficult to operate. So, and because we can't control it, we can't operate it. And if there's something we can operate, right, innovation dies. Everything dies. And this is the defining problem in the industry today. Right? It's defining because every enterprise pursues agility. And all we can do at this point is hold back, be the roadblock, right? Because we need a fundamentally new way of dealing with that with that agility that comes down the pipeline. Right? So, and that is the new reality for all of us here on the operational side, is that we all depend on so many things now that we don't own. Right? So it's a new reality where the environment matters more. It takes precedence over code. Right? In these organically growing federations of services, stability and failure is not due to some defects in individual threads of execution. Right? It's always due to environmental factors, and those are highly unpredictable. Right? Factors like ripple effects, gray failures, resource contention, and noisy neighbors, all these kind of things. Right? Those become the determining factors, right? And this is the new reality. I want to spend a couple minutes on very briefly glossing over existing things, tools, techniques we can use to maybe address that. How can we operate these things, right? And approaches, really, right? And the first one is, hey, let's not do anything. Why do anything? Yeah? Why don't we simply engineer better, right? We get all this chaos happening. It's just bugs. We just, it's a VP of engineering coming in, thumping his chest and saying, I'm going to get my guys or gals to not write bugs anymore, right? So they want to do clockwork. And yes, it works, of course. Yeah? The promise is here, great engineering gives us ironclad robustness. Right? That works great if I deploy something once and then expect it to run at exactly that scale with that hardware underneath for 5 years. Right? And if we can polish it over 5 years. because of course there are going to be bugs. So, but it means you're going to be condemned to distributed systems or engineering, right? So it works on simple and standalone and small applications. It becomes very expensive if the applications becomes bigger, right? Look at Google or Amazon. And often here, developers, engineers think, well, but that's what Netflix and Twitter do, right? They're this rock-solid application, and they do resilience in there and all that, right? But what people don't realize is that Twitter is a simple application. Right? Twitter is not complex. Netflix is a simple application. Their problem is scale. Right? Everybody else in the industry has the opposite problem, where we have generations of integrations of systems, and most of these people don't even exist anymore. Right? They're still productive. They're still part of the fabric, and scale is not a top 5 concern. So a totally different thing. So deciding not to do anything and to just simply engineer better is not a sustainable strategy for service landscapes. Yeah. It gets prohibitively expensive and slow as it grows, and that just means it's going to die, or I can't deploy anything anymore. And I want to map this out a little bit in 2 quadrants. Yeah? Just looking at the architecture, so we can compare all these approaches, right? On the architecture side, like on the left side, single blueprint. On the right side, federated architectures, and then static architectures, dynamic on the top. And then what kind of data is it based on, right? On the right side, and that is, do we look at local data, or are we based on global data? And are we looking at the bottom of the stack or the top of the stack? And clearly, the do-nothing approach doesn't do anything with data. It just sits there in the lower left corner, right? It's very much confined to the single blueprint, the distributed system, and it needs to be static in order to be practical. So next up, monitoring. Monitoring is great. It's essentially just defining KPIs that you want to track, see how they behave, and then correct, and maybe set alerts on it, right? That's kind of like what we do when we teach a baby to walk, right? We know how it should look like, and then we just take, corrective action. And, of course, has a great history in engineering, right? Like on the submarine, of course, you want to know what's the pressure in the oxygen tanks, and how deep are we, and all these kind of things. And that's what you have the gauges for. Those are fixed gauges, right? But that means, clearly, it really only works in places where we can identify KPIs that are meaningful to us. We can get to them, we can measure them, and don't have a proxy variable that's like 5 degrees removed from it. And, of course, only works if these KPIs are static. Right? And as I tried to explain earlier, these service landscapes are highly dynamic, so it's not a good fit. Right? But where does it lie on the map? And yeah, monitoring is pretty universal. You can apply it to anything. But again, it wants a static, because I need to interpret it. It wants a static environment, right? On the data side, it's very local. Typically, we get like host local data, not a lot of globality in there, right? Again, typically at the bottom of the stack. And then that has evolved a little bit more into something that is more high cardinality and high dimensionality, and that's called observability. Observability as a product. There's also observability that monitoring provides. Observability as a product. So that is large-scale application diagnostics. And the premise here is really, this is a waste sorting facility. So the premise is really that I collect all the global data, and then I can drill down in any particular way, and I can find something that is wrong. Right? And yes, that works absolutely if I can instrument everywhere. Right? And if I need or want these deep data, it's a lot of data. It's not called for nothing, high dimensionality and high cardinality. And if I have the time to analyze all that. That is something, again, that we don't really have in service landscapes because they move too fast. I don't have the time. Often in service landscapes, I don't own my dependencies. I can't instrument them necessarily, right? They may come from a different venture partner, a joint venture, maybe a different business unit, a different team that I don't have access to, or whatever. Or they're using a different monitoring or data collector, right? So where does this lay on the map? It's a little bit further up. So it's like, yes, I could use them for federated systems if I have access to them. They still kind of prefer the static side of the quadrant, simply because all the data I unearth, I still need to be able to interpret. And if it's too dynamic, I don't have a model for it, so I don't really know what it means. On the data side, yes, it wants to get the global data, but still global data is comparable only at the bottom layer of the stack, typically. There's another component of observability that is called tracing, and here the promise, of course, is that, oh yes, now I can follow the thread of execution, I can find the bug, and I have right there all the context that I need to diagnose and to fix it, right? And of course, that works in all places where I can actually debug, right? Where debugging is appropriate, and that's not always the case. That most importantly means it's a very local endeavor, right? There's no point of me debugging into services that I don't even know how they're built. I can't interpret anything there. So it's kind of like my horizon of responsibility. Yes, I can trace in that, and it's runtime debugging. Now the question is, why didn't I do this before I deploy it, right? So that again makes it not very suitable for service landscapes. It has slightly different characteristics though, right? So it's definitely at layer 7 on the top of the stack. The data that it collects, that it's based on, it's very hyper-local because it's only looking at a single request, right? On the architecture side, still wants the single blueprint. Federated systems where I don't own the other federated parts, not really suitable for that. And again, once I need comparable baselining, right? I need some modicum of a static system. So last is service mesh, right? And of course, developers always say, well, but isn't service mesh supposed to solve all of that, right? We have these microservice applications, and now it's a dedicated infrastructure layer that does that, right? And yes, so service mesh does or promises four features. Number one is routing. I'm here, I want to talk to a service, I don't know where it is, somebody please route it, right? That's the runtime class loader, the network class loader, the service linking, right? And that is a very decidedly developer-centric perspective, right? Because I'm sitting here, I want to call another service, somebody please does that. And then as you do that, you also use metrics, you collect metrics, you enable people to apply policies that can be changed in runtime over time, and you do encryption. And I love this picture because that's a service landscape, right? And this Baroque garden here is kind of the service mesh, right? It's a very complex thing. Yes, it gets you to the other side, right? And there's a lot of stuff thrown in, like these trees on the side, right? Where, but it requires a lot of Baroque incantation. Like, look at all these ornaments here, right? The YAML that you have to throw in, and that makes it very brittle over time. So it's very difficult to adapt a service mesh to multiple applications, for instance. Yeah? It's just, you can't possibly, anybody who has ever done Apache configs 20 years ago, right, knows exactly what happens if two people try to write it. And the same thing happens on the service mesh side. It is a very complex technology. It is highly invasive, right? You need to standardize on it. You need to optimize your architecture for it, right? And it also tends to be slow. It can be surprisingly slow, right? So it turns out to be a very narrow solution and also not really suitable for these dynamic architectures. Now, where does it lie in our map here? And I would say, I'm starting with data because it's here, yes, it does take local data. It's like the metrics are on the envoys or on the Istio proxies or Linkerd, right? But it's typically on layer 7. On the architecture side, definitely single blueprint. It gets very difficult if you have multiple applications federated, multiple services federated, multiple teams trying to set policies. But it allows reconfiguration, so it is a little bit on the dynamic side. Now, the question, of course, is, are these existing technologies approaches, they're really trailing technologies approaches, right? It's something we used to do and now apply to a new world. And it's not really fit to the new reality. So what we're looking at is who is covering the top right quadrants in these maps. And that's the federated dynamic architectures, right? And the global top of the stack data. And here's how the solution looks like. So we need really an ability in a dynamic service landscape to define the structure that we want to use and govern using that structure, and then to detect and react in real time to any issues that arise, and in order to give the landscape the systemic resilience that it lacks, that we need to add to it, right? And that means like an air traffic controller. This is an air traffic simulation, right? Like an air traffic controller, we need to operate with a mission control mindset, right? Mission control meaning I'm adding something to the architecture. I'm adding actively something, right? So we need to care about the stability and security of the entire airspace, not individual ground operations, right? It's the global environment that matters, not the local logistics. Right? And that requires runtime control. Right? And it requires key metrics for every single flight that we can influence. And that allows us finally to structure and govern, and then to detect and react in real time. So we need mission control operators. And that's what I mean when I said earlier that all successful missions are run, they're operated well. Yeah. There's a certain amount of stuff is automatic, and then the operator is being added to it and adds the human factor, the brain to it. So that requires, as I said earlier, a very small but universally applicable set of metrics that we can base our decisions on. Right? And that's something we call golden signals. And in air traffic, of course, that is the position of the plane, the direction, the speed, the altitude. Right? For us in IT, that's how many requests are running, how long do they take, how many pile up in parallel, how many are in flight at a given time, and how much data are we shoveling. Right? And that applies to any interaction. Text, binary, synchronous, asynchronous, doesn't matter. Long running, short term, doesn't matter. Right? Of course, detecting issues with just a set of golden signals is only half of the story. The other thing is like operational patterns. If you actually want to do something about it, we can't run experiments in production. Right? We need to have very predictable operational patterns that we can apply. Yeah? That are based on best practices. And I'm going to narrate a couple of them because they're going to come up in the case studies in a minute. For instance, bulkheads, right? I may have two different cloud zones, and they shouldn't be talking to each other because A, it's slow, B, it's expensive. But as we all know, misconfigurations happen all the time. So as an operator, I want to insert a bulkhead. But at the same time, critical service should be able to fail over, right? Because they're critical, right? So that kind of flexibility on the policy layer needs to be there. But bulkhead, very useful pattern. Another one, backpressure, right? Anytime you get too much or too spiky or whatever shape traffic on a system, that can cause an earthquake on the other side of your architecture. So if you have the ability to just ever so gently push back and smooth it out, that is a key ability, and can save you from failure. Right? Segmentation is another important one, not just for security concerns, but also if you want to quickly, have something route to a different to a different direction. Same thing, circuit breaking, interesting pattern because most people think about it as a developer pattern, right? I'm writing an e-commerce application. It goes out to fetch a recommendation somewhere that is slow. I'm going to circuit break it. That's a developer circuit breaker. But from an operational perspective, we have the same thing happen, right? I may discover that my Hadoop cluster all of a sudden is like just slightly slower, like 10, 20 milliseconds on average, right? I don't even care why. I just want to right now shed some load. So what do? I insert a circuit breaker that takes all the tier 3 services and maybe only the very long-running queries and just cuts them off. Let them retry. Right? That gives me resilience. And so forth. Quarantining, another one that's going to come up in a second. And so forth. You can also do obviously like fault injection and all that, right? Now, how does this look like? And this is just an example from our console. If you do quick detection and rapid remediation, right? There you would see something like anything that's running auto-discovered on the side, and then you can control. Then there are several patterns in effect here on the right side, how things work. So it's a single, very quick and seamless process, right? Now, jumping to how this actually looks like in the real world, right? And coming back to this example, right? This is actually something that happened at a customer, but it's so generic, could happen anywhere. Something got added, a new deployment got added, so that caused the fan out of an upstream service to change. The pattern would change, right? And now a real heavy request on a cache came after some other request that already fetches it, and that caused the cache to flip-flop. And then result was not full failure, but massive slowness on the other side, right? So the remediation in this case would go the other way around, right? You would first diagnose very quickly, oh, there's slowness, asymptomatic, we don't know what it is. Then you find the downstream root of that. You trace it back to the deployment timeline. And then, of course, you realize it's a new deployment. You apply the quarantine pattern. That means you slightly, reduce the ability how much the new deployment can request, right? You surgically slow that down. Yeah. But that solves the issue. And now engineering can look at it. Why did that happen? Right? Another really funny, great example, and it was published, didn't happen to us or one of our customers. It happens to Target, American supermarket chain. And really interesting because, and this is a simplification, obviously, they essentially run two different environments. One is on OpenStack, and then a huge amount of Kubernetes clusters, right, containers-based. And historically, some clusters were really large, and they had a couple of these really large clusters still hanging around. All the other ones were pretty slow, one application per cluster typically, right? So, and they ran Kafka on OpenStack, other things too, but Kafka, that's what we're interested in. And then all containers had sidecars, logging sidecars injected that would log to Kafka. So that's the situation. Now, what happened is the OpenStack maintainers came in and said, "Oh, we need to fiddle something on Neutron. It's going to be 2 minutes of outage, right? But it doesn't matter because everybody can bridge 2 minutes." So that turned into a couple hours. As it often does, and that meant it was an outage. It came back, it was gone, it came back, it was gone. So Kafka was intermittently available. Right? Now, that caused CPU spikes in all containers because Kafka came back. All of a sudden, the containers, we need a log at the same time as they're supposed to, right? And that CPU spike squeeze the Docker daemon running on each node, right? So all of a sudden, Docker daemon didn't have enough CPU time. Right? So what does Kubernetes do? Exactly what it's supposed to do. Kubernetes declares the node is unhealthy and migrates it to another node, migrates the pods to another node. funny because exactly the same thing happens on the other node, right? With a slight delay, it becomes unhealthy. And so the behavior that everybody sees is, Kubernetes is flip-flopping. What the hell, right? And the remediation would be to simply see the logging spikes on the network links between all these container endpoints and these Kafka clusters, and then exert backpressure, maybe even circuit break long-running requests on that. Problem solved. Right? Third example from the reactive, like how do I fix incidents examples. And this is something we did for a national security agency where they needed a high security video conferencing system. Right? Of course, they didn't build them themselves. They just, the architecture was from them. Basically, different organizations in the government had to be able to talk to each other and internally, but had to be separated very critically. So it's essentially participants going through a gateway, and then all the streams got relayed back out depending on policies, right? And each room separated again within each organization, of course, right? And a bunch of security and governance underneath. So here's how it looked like on the console after a while, where I think I have a button here. All of a sudden, a couple of nodes showed up here, participants showed up that were connected to a bunch of other relay services, and also, showed a lot of traffic. So clearly, something was going on that was kind of a DOS, malicious or not, nobody knew, and absolutely a segmentation violation. Shouldn't happen. So typically, in an old school or a normal operational environment, you would now go and diagnose, maybe, hopefully not SSH into nodes, but it would take a long time. So remediation here would be to simply very quickly see those sources visually, right? And see right away, these guys shouldn't be doing this. No? And then segment them off. Problem solved, right, within 20 seconds or 10 seconds. Right? So, segmentation, important here, right? Another couple examples, and I'm just going to run through them very quickly, is it's not everything. If you can control in runtime, it's not all just about being able to react to something, right? You can also prevent. You can also defend against things, right? And a very innocuous example here is, which we did with a travel portal. Once they were able to quarantine new deployments in production, they could completely get rid of their staging environments, right? Because having runtime control over production deployments as they get deployed and shortly thereafter, right, is enough of a risk mitigation that I don't need this extra staging that, by the way, is not really very relevant either, right? Becomes increasingly irrelevant because I can't even stage the stuff that I have in production. So very helpful in that scenario. Another of our customers is car manufacturer, specifically the connected car unit there. And their problem was they needed to avoid architecture entirely because the applications on the connected car side were so fast moving they couldn't really architect any solution because anything they would architect would be obsolete the next week. And I want to drill down a little bit into that. And that's kind of like how the situation looked like, right? On one side, you have millions of cars, and I call them millions because they're typically all different. And if you think this is a VW Golf, it wasn't a VW. If it's a VW Golf, this Golf is a different model from this Golf, even if it has the same placard on the back, right? Different capabilities inside, different features and so forth, right? On the other side, literally hundreds of applications. Internal, external applications, different versions of applications. And of course, there's a little IoT piece in between that's not that important right now. But essentially what I ended up with is we need to have a service layer in between that is basically optimized for not having an architecture. Right? So these boxes here represent about like 250 services, logical services. Right? What they do is like you can identify access, right? There's direct access direct access. Of course, it's managed. And then there's IoT access. And then there's going for managed access facilities there. And then there's a data read-only access, basically, where I don't have to control. I just need to read. And so data is being pulled through various protocols and various stages. And every connected car group does this the same way. And it enters a series of like cascading data stores, right? And then we have, of course, like a bunch of like analytics and diagnostics and plausibility and other auxiliary services. And any data query that comes in goes through a set of query planners, and they fetch the data from whatever it is. That is the architecture. Now, when a new application comes in, and it happens every week, needs a new service, what happens? What is the cloudy way of doing it? You create a new service. And typically that's just a little bit, it's just a facade to an existing one that adds a new feature. Right? So it's not a feature flag in that service that has the potential of causing disruption. It's a new service next to it, because it only costs like $2 a day to run. And that provides a new feature without disturbing anything else. Right? So we help them with runtime control in that regard, right? And a bunch of patterns, like absolutely every deployment was quarantined, bulkheads between the protocol tiers, and so forth. But that is the interesting use case here, right? A third example I want to give, and that's the last example here, is that work we did with a cloud provider where they provided individual cloud environments to the customers, enterprise customers. And they started with SDN and then tried to shoehorn the SDN solution with the help of the vendor to provide even more fine-grained control, right? Because it becomes very, very difficult, right? You have individual customers, and now they use those cloudy Lego blocks that you have, and these Lego blocks, but now are, mapped onto a bunch of base services, right? So it's a very very entangled system underneath, and that requires not just segmentation on the top. It also requires pretty flexible bulkheads underneath, so that a noisy neighbor here doesn't affect the next customer indirectly. Right? So in summary, what I was talking about is and before we get to the takeaways, what I was talking about was the agile operating model that we all live under now, right? And the agile operating model is really like small teams, cloud, creating a lot of services in parallel. That creates a service landscape, right? And now with the added control of a traffic controller and mission control operations, that makes the entire organization agile. Right? And then I talked about what is a service landscape and how it is a organically growing federation of applications and services. And then talked about how this is a new reality, because in that new reality, the environment takes precedence. It's not about debugging code. It's overwhelmingly more about getting the environment to be stable. Then I talked a little bit about existing approaches we can bring to that problem of dynamic architectures, and then sketched out a real solution. How would the actual solution look like? What does it need? And that is hinges around rapid remediation. Rapid remediation, of course, needs real-time visibility based on golden signals, and it also needs real-time remediation based on operational patterns. And then I gave a couple examples. So what are the takeaways? And those really depend on where your organization is in the stages of chaos acceptance. Right? And if you're in stage 1, which I call the denial stage, right? This is where you come in and say, oh yeah, there's no chaos really, it's just, we have a couple bugs, right? That's fine. It just condemns you to micromanage engineering now. You need to look at every single engineering decision very carefully, and you're going to be back in that state. You're going to stay in that stage, right? You're not going to get out of it. But there's still things you can do on the developer side. You can tell, you can work to have your developers add compensation strategies to these calls, right? A lot of engineers, when they build distributed systems, just call out, right? You need to, even though it's a distributed, robust, supposed to be robust system, you need to have compensation strategies. What happens if this call doesn't come back? What happens if it takes too long? And these kind of things, right? The other thing is shift left, right? Heavily invest in unit testing because you're going to need this later, right? That's where it's high value and cheap, and it's very expensive and low value afterwards in production if you want to trace, right? That's what you can do in this stage, right? Now, if you're in stage 2, which we call bargaining, right? That is where your engineering department says, well, yes, the chaos is there, but we fight it with standardization. And that's the organizations that re-platform, right? They say, well, yeah, there's all this stuff happening, but yeah, we're just going to bring the platform up and now it's manageable again, right? It works for a while, right? It's definitely Golden Masters thinking, right? Like 20 years ago, we deploy a Golden Master, and 5 minutes after I created the Golden Master, a new package was released. And similar things happen on the platform side as well, because new technologies come up. I know of examples where enterprise-wide, everything was rebased on Kubernetes, and then function as a service came out. That didn't fit the mold. Not a good example. Not a good position to be in. Still, developers can do something at that stage, and that means that is particularly avoid distributed systems. Distributed systems engineering becomes an anti-pattern very quickly in these larger dynamic architectures. There's no point in 2020 almost to try to solve any distributed systems problem, right? It's either already solved, you're using something that does it, like Cassandra, or you shouldn't be doing it. Yeah? Number 2 is, instead, do eventual consistency all over the place where you need it. But when you actually need accuracy, when you need security, safety, and a safe return of something, resort to redundancy. Right? Use a calculation 3 times, yeah? different paths, and that gives you more nines on the return. Also use plausibility to catch things that can't be right. Tell developers to invest in these things. And, of course, invest in building resilient foundations, like any base services that they can build that have inherent resilience in it are going to pay huge dividends later. So what happens when you realize that all my platforming efforts only lasted like 6 months, and now we're back to the chaotic behavior? And that's stage of depression, right? Where you say, well, shit, that is now real, there's chaos going on, and we can't do anything about it, right? As an operator, the only thing left to do that you can do at this point is push back. We can't take it on. You're coming with a new deployment. Please go back to the line here. I need to test you. And by the way, the line is like 6 months long, right? So you're condemned to stasis. You're a complete loss of velocity. And that ultimately means, again, innovation dies. So what can you do at this point? And there's only one thing you can do, and that means accept the chaos. Accept that you need to defer a lot of things that you used to do in code, you need to defer to runtime control. And that gets you to stage 4, which is the acceptance stage, and where the chaos is actually controlled. And there's a couple things now we as operators can do. Right? Number 1, realize that code doesn't really matter anymore. What really matters is the environment, environmental factors, control for those. Any defects in code should be unit tested. And frankly, they're easy to test. Code is really easy to test. Right? What's not easy to test is load testing, things that happen in production. Right? Shift left radically. Push everything back to engineering. Invest in rapid remediation cycles. Right? I've talked about this many, many times. Identify golden signals, and figure out which kind of operational patterns you want to have in your playbook that you can apply quickly. Yeah? No matter what technology you use. Absolutely do not even start thinking about root causes. There is no such thing, right? It's like a dysfunctional family. There's no single person that's at fault. Right? Service typically works totally fine in Unity. As soon as deployed, something else happens. Or 5 minutes later, or 10 hours later, something happens. And it only happens then. So those are flukes. It doesn't pay to chase them down. And besides, root causes are typically like a confluence of factors. So there's never just one root cause. So instead, remediate. Don't even look for the root cause. Be the triage nurse. Right? Somebody coming in to an emergency room with a temperature of 45 degrees. You know what you do? It doesn't matter what the cause is. Right? That's for later. That's when you tell the specialist doctor, hey, can you figure out what that is? But first, he gets the injection or whatever it is. I don't know what you do. What do you do when you have 45 degrees? Then also absolutely do not agree to execution debugging. Do not agree to engineers instrumenting workloads for tracing. Nobody should be tracing. And if you don't know what your services do, and you need to know which kind of services they are hitting, you're doing something wrong. You're coding in distributed system, right? But that doesn't work in these architectures. So there you have it. Oh, sorry, architected runtime. Yeah. So realize that a lot of what we used to do as architects is now operations. Right? Architecture and operations are both runtime functions. Yeah. So there you have it. It's like 6 takeaways while you're still waiting to accept the chaos that you can have your developers do. And then 6 takeaways for operations guys. And that includes, of course, anything DevOps, any SRE, and even security operations guys, right? And those apply to all decentralized architectures, not just microservices. So from the mainframe all the way to serverless. So architecture is becoming a runtime activity. Now, to close the loop, we're almost done. Apollo 13 didn't come back to Earth because it was well engineered, right? It returned happily to Earth because it was well operated. It was operated well. Right? And this mission control mindset is something that the Southwest guys didn't have. They didn't have the ability to quickly see that this router had billions of packets coming in and nothing coming out. Right? They didn't have the ability to exert back pressure against the systems for a while. Right? If they had seen within a minute or even 5 minutes that this thing is not routing, and then had the ability to push back, nothing would have happened. They wouldn't have had to restart services, right? So unfortunately, they didn't have the ability. But today, as operators, we can do that, right? We need to absolutely invest in the capability to operate the chaos, to control the chaos, right? And that means invest in the ability to view golden signals and apply operational patterns. Be the team that enables the business to be agile. So, and if you think that your organization struggles with the chaos and you want to talk about this, I would more than happy, totally irrespective whether you want to use us or somebody else. It's my favorite topic, obviously. Find me like outside or email me or hit me up on Twitter. My DMs are open, so you don't need to be connected to me. And that's it. Thank you. Right up to the hour.